Good afternoon, everyone. Luckily, I prepared my presentation, my slides, at least in Italian, but okay, I'll try to present in English. So the topic that I'm covering is the topic of cumulative damage in unreinforced masonry buildings during a seismic sequence. This is a topic that generally is neglected, at least in vulnerability and risk analysis. Now, this work is part of a larger project, which is a return project aimed at finding or defining multi-hazard maps, risk maps, for the definition of optimal intervention strategies, which, as you can see from the acronym, it's a collaboration between the Youth Center Foundation in Pavia and the University of Napoli Partenope. Now, one of the tasks of this project is aimed at defining the vulnerability of buildings, bridges, and industrial plant, accounting for the damage accumulated during a seismic sequence. Now, the case study that we defined into the project is the one of the region of the Irpinia region, which was eaten by an earthquake in 1980. Now, the goal of the work that I'm going to present in this presentation is the definition of a methodology to study the vulnerability of masonry buildings, accounting for the cumulative damage. And the goal is to use the results of this methodology in risk analysis or damage scenario analysis. Now, the first step is the definition of some prototypes, some building prototypes that were derived from the survey of the historical city center of Benevento and of another suburb, which is the Rione Libertà, survey that was done in the framework of the Traiano project. At the end, we came out with these 4 prototypes, characterized by 2-3 floors, floors that are rigid or flexible, and different building ages, construction ages. In all the cases, structural details are present that are preventing the formation of out-of-plane mechanisms. The definition of the case study involved the definition of a village located into the area that we are considering. Defining the village means defining the number of buildings belonging to the 4 prototypes and the location. Also, characterization is, of the location is available. The next step is the definition of the seismic hazard. Now, to do that, we used a spectral element model of the area that was developed by the group of the Politecnico di Milano. This model has the peculiarity of modeling all the seismogenic sources in the area. And it was used to generate first an event which is exactly equal to the main shock of the Irpinia earthquake. And by applying this model, it was possible to generate some acceleration time histories in different points of the area, and in particular in the location of our village. We then applied other 3 times this model, this time simulating plausible aftershock event characterized by decreasing magnitude. So in order to have a sequence of 4 events. In all the cases, the generated acceleration time history are assumed to be on rock site, and then we applied local response analysis, site response analysis, to having the time histories on the real soil. So the next step is to model the buildings. We consider just the first prototype, and we model through equivalent frame modeling strategies, implement using the software Tremuri, allowing to perform nonlinear static and dynamic analysis, adopting advanced macro element with a mechanic-based formulation. Now, the prototype is characterized by 3 stories, rigid floors, and tough masonry with mechanical properties obtained from calibration of experimental tests. The next step of the work involved the definition of state-dependent fragility functions. Now, state-dependent fragility functions are representing the fragility of a building in a certain state of pre-damage. To define these curves, we applied an existing methodology, the one proposed by Moyano et al., which is involving several steps. Now, the first step is the performance of nonlinear static analysis, monotonic nonlinear static analysis of the whole building to define the thresholds corresponding to several limit states. Now, we consider in particular 4 limit states ranging from operativity limit state to collapse. Now, here you can see some results for the two main directions of the building. One direction, the X direction, is characterized by a more brittle behavior, so a lower displacement capacity, characterized by concentration of damage into the ground floor. Whereas the Y direction is characterized by a more ductile mechanism with a larger displacement capacity. Now, this type of analysis was used also to define some pre-damage states. Particularly, 17 pre-damage states were considered, the DL0, which is the undamaged condition, up to DL16, which is the largest one. And we defined this simply considering the range, the displacement range between two damaged states and divided it into 4 bins. Now, the second step consists into the definition of an equivalent single degree of freedom system. Now, the system defined by Graziotti in 2016 was adopted. This is a simple model implemented in the Tramuri software made of 2 macro elements, one representing the shear and the other one the flexural response. The definition of this simplified model involves first a static calibration, which is aimed at defining the geometric properties, the mechanical properties, and the axial loads of the two elements in order to reproduce the cyclic static behavior of the building. Whereas the second step is a dynamic calibration in which the goal is defining the damping parameters, Rayleigh damping parameters, with the goal of having displacement demand which is as possible, as similar as possible as the demand of the multi-degree of freedom system. So in this way we were able to define 2 single degree of freedom systems, one for each direction, in DL0. Now, the third step was the generation of these models also for the other 16 pre-damaged states. And that was done simply considering the undamaged system, imposing displacement up to the thresholds corresponding to the beginning of the considered pre-damaged state, and then using a complete cycle of imposing a displacement and then coming to 0. All the single degree of freedom systems that were defined this way were used to perform a cloud nonlinear dynamic analysis, adopting the almost 500 ground motions taken from the SIMBAD database. Now, the comparison between the demand obtained this way and the capacity defined previously allowed the definition of fragility functions for the 4 limit states and for all the pre-damage level. Now, here you can see some results on the right for 2 directions and for 2 limit states. The set of curves is representing the curves corresponding to each pre-damage state, and as expected, you can see that increasing the damage state corresponds to an increasing vulnerability. Now, the final stage of the work consisted in the analysis of the building subjected to the entire seismic sequences. So the couples of ground motions that were generating from the hazard model were used to perform a nonlinear dynamic analysis of the building. Firstly, the original sequence, characterized by decreasing magnitude of the events, was adopted adopting also the real soil conditions. As you can see from the results in terms of top displacement time history and hysteretic curves, the displacement demand is decreasing with the increase of the sequence. Now, looking at the results in terms of damage states at the end of each event, you can see that unluckily the building is obtaining the largest damage level with the main shock, so at the first event of the sequence. So there are essentially two problems. One is the fact that we are attaining the highest limits, the highest damage level, so it's physically impossible to increase the damage state during the sequence, and the other is the fact that this damage state is not increasing. But these are problems more not of the methodology, or mainly of the case study. Now, these results will be used later on in a future step of the project to perform risk analysis or damage scenario analysis in each phase of the sequence. So the idea is to essentially use the hazard of the main event, the main shock of the first event, with the fragility of the undamaged state, and then using the hazard of each event of the sequence, using the fragility corresponding to the damage level at the end of the previous event. And this will be done using the Euclid platform provided by the Youth Center Foundation. Now, in a case like this one represented, in which there is no increase of damage level during the sequence, this will mean that there will be the possibility of evaluating the effect of cumulative damage only in the first two phases. Now, to see the effect also in the other phases, we try to manipulate a little bit the problems. Firstly, we inverted the order of the events of the sequence, moving from a sequence with events with increasing magnitude. In this case, which is the case B represented here, in this case you can see that we are able to avoid the problem of not having an increasing damage level during the sequence. We then tried also to modify the site, the soil conditions, so moving to a rock site and maintaining the original sequence. Now, in this case, we were able to solve the problem of the fact that we are attaining the largest damage level at the first event, but the damage is not still accumulating. So, coming to the conclusion, to sum up, in this work, we first defined a case study in terms of hazard, number of buildings in the village that we consider, and modeling of the prototypes. We then defined and applied a methodology to study the vulnerability of URM building, considering the cumulative damage during the sequences, which involved the two steps: the definition of state-dependent fragility functions and the analysis of the building belonging to the sequence. And finally, these results will allow to define the effect of cumulative damage when applied for risk analysis or damage scenario analysis. With this, I've concluded. I want to thank you for the attention.